All right. Happy December 1st. For the first time in my life, I own an advent calendar. Yep. Minecraft. Zeke and I are doing Minecraft. They were selling them at Alaska Ship or Safeway. And when I Amazoned it, it was cheaper than Amazon to get it at Safeway, which doesn't normally happen. All right. So today, there's no way around it. We are going to get some kind of, I don't want to say boring, just because if I say it's boring, then maybe it is. But we get some theorems that we're just going to have to knock out. So in 4.2, we are talking in this section about extrema and critical numbers. Extrema and critical numbers. And I will be honest with you guys and completely transparent. When I look this up, it is not pronounced extrema. I think I say it wrong, but I think it sounds better. It's extrema when I ask how to pronounce it. Do you guys see extrema or extrema? Okay, I will start saying extrema. I will try my best. Cool. All right, so right off the bat, if we wanted a really formal definition, and we're going to get a rigorous formal definition of these, let's define these. Let's give ourselves extrema, sorry. Okay, now, they come in a couple different flavors, right? We can have minimums and maxima, or minima and maxima, and they can be local or relative, or absolute and global. Like either way, we get all those different combinations. If we're looking at these, it shouldn't matter necessarily whether we're saying absolute or local, but we're just going to define both of them. So definition-wise, for extrema, we get two of these. We're going to say that minima, or minimum, and minima. Okay. For this, we'll just make the claim and you guys are going to help me finish this. I'll switch colors here in a minute and we'll have another one that's maxima here, just so you know. Okay. So for our minima as an extrema, gross, everything feels weird when I say it. Here we go. We're going to say that f of c is a minimum. And I'm going to write mathy here for a second. F of c is a minimum if, and let's just think of what it means to be a minimum. It needs to be bigger or smaller than all of its neighbors. So that means f of c had better be smaller than or equal to, I suppose, and there's a weird little part of this, f of x for all x around. Now, we could be more formal than this. We could have said that there's some small interval, we'll call it I, where this is true. But as long as you can see that with all the x's around it, this is smaller than everything else, it's a minimum. Okay, it's exactly what you guys identified on the graph. Can we use similar language to define for ourselves a maximum? Or a maxima? What is our statement going to say? And we're going to be much shorter with this. F of c is a max. So we're going to write this much. F of c is max. If, or if and only if, what? If it's a maximum, what would that other side of the statement look like? F of c, whatever we're plugging in, must be greater than or equal to all x. For all x around. Okay. Every single time, this is just what we're looking at. Is it bigger than everything in some region around it? Is it smaller than everything? Now, what's weird about this is not everything will have minima and max. We have to be careful about it. So if we look at just some goofy situations, I'm going to sketch 3 small graphs, and I just want us to be aware that there's some wonky stuff that could happen. So 3 graphs really quick, and they're not going to be big. They're all going to be in quadrant 1 because it's easy to graph. And I'm just going to copy and paste this 3 times. So x and y, and we'll do this, x and y, and we'll do this, x and y. Fantastic. Okay. Now, as we look around these, there's some weird little things that happen, and we're going to see them here and now. The first one, let's say that I have a function that goes, I don't know, let's say it starts with an open circle over on this side. So maybe there. And it dips down and comes up to here. Okay. Now, this interval is half open. Just so, like, language-wise, it's half open and half closed. Which side is this open on, do you think? The left or the right? Which of these represents open? The left. Do we include this point? No. So if we were looking at like intervals and stuff, would this be a parenthesis or a bracket? Parenthesis here, and it feels strange to do, but I do think it's good practice. I'm going to put a parenthesis right here, and I'm going to put a what over here where it actually does include? A bracket. So this is a half open, half closed set. Does this thing have any extrema? Like, can we all agree it has a minimum? And it's probably right here. Okay, min, that's easy. It is smaller than everything else nearby. Here's the weird part. Does it have a max? So it's a weird idea, right? This min is obvious, and this one, I think that you're just as well to say no or yes, right? Based on the language that we have so far. It turns out in this situation, we're just going to default to this. If we aren't even defined on the other side, we're okay to say it's a max. Okay, deal. It's just we have to accept it. This is just part of the definition. If it's closed on one side, we can't check the other, we'll still call it a max. Okay, with that said, what about this one? We'll do the same graph. Let's make one little change. This is a completely open interval with a parenthesis here and a parenthesis here. Does this one have a min? For sure. It's roughly the same spot, and I'm going to close the door because I think we're going to hear wrestlers and stuff because they'll be in and out. All right, here's a harder question. Does this one have a maximum? Okay, we'll just go with gut feeling because I know it's like not super clear. If you think there is a maximum, hand up. Fair. Okay, now as we look at it, just checking them. I'm just going to make up a number. We don't have to write it down. But let's say that this is at 20. Like right here, right at 20. How close to 20 does it get? So if you pick really, really close, like no matter how close you wanted, could I get closer? Yeah, because that's how numbers work, right? Like if you pick 19.99999, that's 5 of them. I'll say, oh, I'll just get closer. It's 19.999999. And I'm closer now. Can we ever stop doing that? So no matter how close to 20 you give me a number, I can get closer. Means that, gosh, we can never decide that there is a maximum. There is no maximum here if it is open on the max. If it's closed, it's okay. Closed K, you might just say. Never mind, that's terrible. Don't use that one. If it's open, All right, one more wonky one. Now I'm going to close both of these there, and we'll define that point right there. Does this function have any extrema? I think there's a maximum, and there is a maximum on the right side at that closed point. Is there a minimum? Because exact same argument, right? If whatever number this is, you try to get as close as you want. If I can get closer, and then we can go back and forth, and we never stop, we're never going to decide and agree upon what is the actual minimum value. So in this situation, as long as it's closed, we do have a maximum here, but this guy right here is not a min. Not min. Okay, these situations are wonky and we have to deal with them. What we wind up getting is that it's these issues, right? It's the open circles that make this weird. If there were no open circles, would it be a weird question anymore? Probably not as weird. Like the endpoints are kind of strange. We get our first theorem. So I'm going to see how your book calls this. Nope, we don't even see it. Okay, for this, we'll just define our theorem. And we're not going to give numbers to these. This is called the extreme value theorem. And you will never see me write this again. The extreme value theorem. EVT. Okay, extreme value theorem. Super duper easy. Okay, if you give me a function, and we'll just say it's nice, we'll call it f of x. If some function f of x is continuous on the closed interval from a to b, then there exists, and remember that backward capital E is just a shorthand for there exists. If f is continuous on some interval, then there exists a min and max within the interval. And I'm just going to say a min and max. Now, you do get some weird situations here, because I can think of continuous functions that maybe don't do any curving, right? If it's a horizontal line, for example. This function, it seems so wonky, but we're just going to sketch it. This is a unique situation, but it's worth talking about. If we have this function, and we'll just say it's closed from here to here. This is the weird little counterexample, but luckily for us, we have a way around this. Is there a smallest value? If I say what's the smallest value that function ever gets to, can you tell me definitively that there's a number? Like, it's the pink one. And let's just say my scale is perfect. Do you guys agree that that's at 1 on that scale? So what's the smallest value that function ever gets to? 1. If you can answer that question and I can't get any closer to it, like we can agree there's a min, right? And it's weird, but there is a minimum. It's at 1. What's the maximum that function ever gets to? 1. So its maximum is also 1. And that's the one weird situation. If you look at the very first things that we wrote today, we said it's a min if f of c is less than or equal to. Here's our or equal to situation. That's where this is being covered. Or equal to allows for this to exist. Okay, that's a weird one. The big takeaway is that you'll be able to find mins and maxes. Okay, now we looked at local or relative mins and maxes. Do we need to redraw that picture to talk about them further? Because we're going to move on past just this stuff. We're going to be very similar to what we did for our bell ringer. Do we need to redraw that picture, or are we all okay with Extrema, sorry. Do I redraw it? Okay, so as we're looking at these, turns out there's something calculus related. So we're just going to jump right in. So here we go. Let's talk, and this is going to feel like a different section, but it's really the same thing. Let's talk some critical numbers. Now, whether we call them critical numbers, I like to call them critical values, but they're, I think, interchangeable, strange. How does your book say it? Critical numbers. Okay, we're going to leave this blank for just a second, and we're going to come back to this idea of what happens on a graph. And we will sketch at least a brief one. It doesn't have to be the same thing. But I want you guys to help me with this idea of extrema in mind. I want to think about a function, and we're going to start with a theorem immediately. So here we go. We'll leave a definition, super easy. And our theorem right off the bat is going to be theorem relative extrema. Relative extrema. And the actual theorem does not have a name in your textbook, just so you guys know. In a geometry class, I focus pretty hard on calling it theorem 4.2 or whatever, so we can see where it is in the book. These ones, they're not numbered very nicely, and we don't always include. Anyway, relative extrema, check it out. You guys can pick out extrema by like sight, I think. Do you agree with that? If I give you a graph, even if you don't know the graph, you can say here's a min and here's a max. Okay. I want to think about the calculus part of these. So our critical numbers we'll define here in just a second, and we just need one really quick and easy graph, and it doesn't have to be wild at all. Let's just say that it does this. Here's a graph of f. Does f of x, or f in general, right here, does it have extrema? Any? No mins, no maxes? I can't tell, you might have just been scratching. There's a min, right? I can see that is it local, absolute, or both? Both. This is the lowest value it ever gets. Now, what I want to do is I want us to think about the calculus version of this, because we can all identify it. So we're just going to say, I'm going to put this value c right here, just so we have something to talk about. Okay. How would we decide that this thing, with a little bit of calculus, has a minimum? What do we know about the derivative here? Or what do we know about the derivative as we get closer to it from either side? I'm going to give you guys like 30 seconds, talk it out. How do we say that, what happens with the calculus when we agree that this is a minimum? How do we look at it through calculus instead of just the graph says it is? I'll give you guys a second. Think about derivatives and what they do. All right, so looking at this, what do you guys think? I'm open to ideas. Notice I didn't say good or bad, just ideas in general. Something to do with calculus. What do you got, Rafa? Ooh, so I like that. Don't draw all these. I'll draw the one that I want you to draw in yellow. Do you guys agree that's the tangent line right there? And if I make up a number, maybe it's like -1. What is it here? -1/2 maybe. What about all the way down here? And I'm going to get even better with it. And I guess that's the one I'll draw. If I drew the tangent line right here, what would it look like? 0, right? It would have to be this. And then it starts increasing again. It could be 0. There's our first one. I like that, Rafa. Now, I've drawn a nice function. I'm going to draw another graph on this that has another min, but I'm going to do it on the same scale. What if I draw this all of a sudden? Because that function, I think also, we'll call this one g. Does that function also have a minimum at x equals c? That's smaller than everything else nearby, right? But can I use that same idea for the derivative here? Is the derivative defined there? No, but it's still a minimum, right? So we have two different things that we're going to notice. So what we're going to do is tie this in with the calculus, and we're going to write out this theorem. We will say that f of x has an extrema. F of x has extrema. And I'm just going to say it has an extreme. I lied. Extrema makes sense. At x equals c, if and only if. And we saw two situations just now where this could happen. What do we know about the derivative of f if we get down to that extrema? If I were to take f prime of c, what's the slope of that? 0? Yeah, certainly. Now, it could be a min or a max, or f prime of c, and what would it be on the purple graph? Because it's not 0 anymore. I'm going to change it from equals. What would we do if we try to draw the tangent line at that sharp turn? Can we? Does not exist. So give me a mathier version of that. F prime of c is undefined. Okay. Now, language-wise, critical numbers, easy to define. We can say that this in our theorem, another way, we just haven't defined it yet, f of x has an extrema at x equals c if and only if, and we're just going to say x equals c is a critical number. And we're going to sneak back up, and we need like 3 or 4 words is all to define this critical number. So check this out. There's 2 things that led to me saying that this thing is critical and why it's important, like, to this problem. If the derivative is 0 or undefined, that's where this happens every single time. Every single time. Which means critical numbers, super easy. We'll just say it's, realistically, it's a set of numbers, but we'll say any x for which f prime of x equals 0 or undefined. That's it. If you give me any function and you can find where the derivative is 0, maybe, just maybe, you've identified an extreme. If you've identified a place where the derivative is undefined, maybe, just maybe, you've identified an extreme. Now, we won't know for sure, but we're going to use these critical numbers to help find out. Should we take a really quick, like 1-minute brain break? Okay, it's super chill. I'm not going to do anything. It's just chat with your friends. Say something good. Compliment each other. You owe each other a compliment. Not of it. All right, check it out. We have some critical numbers. Did everybody get a compliment just now? I'm proud of you all. I don't know if that's really a compliment, more of a sentiment, but okay. So check it out. Critical numbers. Here's our goal. We are going to do a bunch of stuff in this problem. Now, historically, I've split these examples up into a few different parts, but we are going to consider, and we're going to do like 3 or 4 parts. We're going to consider a function together. And let's deal with this. No, that's too easy. Oh, that one's much nicer. I would probably switch. How much room do you have left? I think the whole example will probably fit on my screen. I don't know. I'm not doing a crazy amount of stuff. Okay. So I want us to consider the following. We're going to look at f of x, and we're going to look at it as the cubed root of x. But we're only going to look on the closed interval from -1 to 1. So we have one singular function, and here's the interval on which we are working. Now, I don't want to have to graph it. If you guys want to have to graph it, you do you, make a table of values, graph it. I'm not going to. Here's all I want to do, and we're going to break this into some smaller parts. I want your guys' help on A. We're going to find, and you're going to see this shorthand over and over, but if I write this, crit octothorpe S, what do you think I'm shorthanding? These are the critical numbers. Okay, there's our first step. Where do we get our critical numbers from? The derivative, and then we set it equal to 0, or we see where it's undefined. So to find critical numbers, let's do exactly that. We need to first get f prime. So before we do f prime, just in case, is there a better way that I could write f? X to the 1/3. And I think that was Riley or Kalisha or Delilah. I couldn't tell exactly who, but I agree with you. Now that I've written it like this, can I find f prime? What's f prime? One-third. I agree with that. Lack of confidence here. X to what power? -2/3. We subtract 1. Okay, so I'm going to write this one more time because now that we're here, like we have not been simplifying everything throughout the problem, but now that we need to know, is it undefined or where is it 0, maybe it becomes more valuable. So let's just rewrite this. F prime of x is equal to 1/3, and it's the cubed root of x squared. Okay. Now, 2 things, and this is like an old pre-calc idea, but I want to note and notice a couple things. Can you ever make this 0? You say yes, Fern. I don't know that I agree with you. To make a fraction equal to 0, what part has to be 0? The top. What is, or the numerator, but what is the top always here? Is it ever, does it even have an x that I can make it 0? So the numerator can never be 0. I'm going to make this comment. Numerator, never 0. And I'm just going to say can't be 0. And we could say can never be, however you want to word it. But if there's no variable up here, not a chance. So there's no critical numbers that come from when it's 0. Is there any place where my function, or my f prime, which is a function, any place where this is undefined? There's only like 3 things that we worry about in here that we've seen that can make a function undefined. Can you give me one of them? Dividing by 0. I don't care if it's 1 or not. If you're dividing by 0, it's undefined. Any other options? You can't take a square root of a negative. That's undefined because you need the imaginary numbers. There's one more. Something to do with logs. If you're taking the log of something, it has to be positive. The argument must be positive. Those are like the 3 situations that we worry about. And there's some other ones that kind of sneak around in there. But I'm just going to notice something. When is this undefined? Undefined when denominator equals 0. Is there an obvious value for which that happens? Rafa says 0. Are you guys cool with that? Now, if you weren't quite cool with it, we can just take this whole thing, 3, and I'm going to write it x to the 2/3 at this point just to do this. I'm setting the denominator equal to 0 just to show that the math does work out nicely. Help me solve. What do you do? Divide by 3, so I get x to the 2/3 still equal to 0. I agree with you. Now what? I'm going to take each side to the power of 3/2. I then get x equals 0 to the 3/2, which is what? 0. This is undefined. So what we have just done, in whether you show this work or not, is we just said critical values, or numbers, x equals 0. That was the only one. It was undefined there. Now, this means that we could have a maximum here. We're not sure yet. So all we're going to do is just check any places where it could happen. If we look back at our pictures, is there a difference between using brackets and parentheses? The 3 graphs that we drew at the beginning, if they're both brackets and it's closed, then it could be at the endpoints as well, right? So right now, here's where we're at. I know that if this function has any extrema, it's going to happen at one of 3 places. So on B, and we'll just make this nice, check f of endpoints and f of critical value. And I'm going to use val just because I don't like to draw the octothorpe, the hashtag, the pound symbol, whatever you call it. I don't really like this either, but that's okay. Critical value is probably the language that I will use, just so you guys are aware. So let's check some stuff. And really important places where people get goofed up with. On the board, I have f and f prime. What are we trying to check on B? Is it f or f prime? We're just checking f. So let's check them real quick. If we check f of, give me an endpoint. -1. And is that left, right, or critical? This is the left. Okay, so we'll just make that note. And let's try it. What's the cubed root of -1? -1. Okay. So here's my left. That's my left endpoint. What else should we check? F of what? F of 0. And yeah, let's check that critical value. F of 0. And I wish it was easier. Can you guys see that blue okay, or is that a poor choice? Okay. What's f of 0? 0, because remember I'm plugging into this guy. The cubed root of 0 is 0. Okay, this one was critical. And one more to check. What should it be? The right side. And what is my right endpoint? 1. Okay, so what is f of 1? 1. And here is the right. Now, in just these values, we know that the only place that an extrema can happen is at one of these three. Can you guys identify the minimum and the maximum here? This is the what? Minimum. So here we go. We'll make this statement really clear. F of x, and I'm going to write it in purple, and we'll do it just here. From all of this, here's my implication. F has minimum at which point? -1, comma, not 0. When I plug in -1 into f, what did it spit out, JJ? Good. -1, -1 is my minimum. How about the maximum? At 1, 1. Now, it turns out in this problem, the critical number or the critical value didn't have any bearing. Why was it undefined then? We can have derivatives undefined for a few reasons. One, it could be the sharp turn, it could be the cusp, it could be the asymptote stuff. There's one more possibility. Remember that these are just slopes, right? What's an undefined slope? Straight up and down. Is there situations where tangent lines would be vertical? For sure. Like, and you said absolute value. So I would say that's a sharp corner, but I like where your head's at. Let's look at the graph of this, because you guys might not recall what x to the 1/3 really looks like. But I think that we'll see something, not YouTube. That was a weird little x to the 1/3. If I were to draw the tangent line right here, is it going to be vertical? Yep, and it is undefined. Now, if we only look for x in this little range, -1 is less than x. I need the brackets, curly brackets. -1 is less than or equal to x is less than or equal to 1. Do we agree that this certainly looks like it is the highest value at 1, 1? And here, it's not a max or a min, but it could have been, right? We didn't know until we checked. And is this the minimum value? Boom, we can get all this information without ever having to graph every time. And in fact, we'll keep building this up, and it will get better and better and better. And eventually, we'll be able to graph without ever having to think about values and making tables, because we'll have everything that we need to be able to describe it. Does this seem super duper hard? Can I give you one that's going to be a little bit harder? And I ask if I can, but I'm going to, obviously. So let's do B. And by let's, I mean I want you guys to try B. Okay, so we're going to, sorry, this is not B, right? It's just another example. We'll just call this example. Let f of x equal, and this one's just a nice one, 5e to the x minus e to the 2x for all x in the closed interval from -1 to 2. All I want you to do, and I'm not going to break it into A and B this time, all I want you to do is find Extrema. I'm going to give you guys a moment. On the first problem, all I did was I split that into 2 different parts. I said find the critical numbers and then check them. You're just doing that in one part A this time. Cool. I'm going to give you guys a moment before I start working it, but I bet it works the same way. You need the left endpoint, the right endpoint, but you also need the derivative. Cool. I'll give you guys a moment. Turn them back in here. We're going to look at factoring stuff really briefly, just to make sure that we can all agree on something. And you're going to see some language. We've not spent a ton of time factoring because we've only been concerned about the derivative stuff. But now that we have to solve them, I think it makes sense that we'd want to be able to simplify and factor down because they're going to be more manageable to work with. Okay, so as we look at this, we need to set this equal to 0, right? Like that's the goal. So here's f prime. We're going to set it equal to 0. And is there anything that I can factor out of here? E to the x. Now, it's weird to do this, but maybe not weird. I'm going to factor out what I call the least power. So I have e to the x and e to the 2x. Do we all agree that this is the smallest power? So we'll factor it out. What does it leave behind? 5 minus 2, e to the x. Because when exponents multiply, they add, right? So e to the x times 2e to the x is 2e to the 2x. Okay, now this little step here, I do want to really highlight that language. This is least powers. And you will hear me say that again, because when we get super ugly expressions with like x to the 1/3 and x to the negative 4/3 and ugly numbers like that, we're still going to do the same thing. We're just going to factor out the least power of x and have to work backward to get the rest of it. Okay, at this point, we have how many factors identified then? 2 of them. Is e to the x ever 0? 2 to some number, you can't make it be 0. You can make it be really close to 0, but never 0. Can't do it. Never equal 0. Okay, bummer. This one, we might need a little bit of scratch work. Let's try to make this one equal to 0 and see if we can do it. So if we had 0 equals, and I'm just setting this factor now, 5 minus 2e to the x. What should we do? Say it again. So I could subtract 5. Could I just add 2 also? I'm going to do 2 things. I'm going to add 2e to the x, and then I'm going to divide by 2 in the same step. So if I added it and then divided by 2, I get e to the x equals 5/2. Do I need to show that intermediate step? Okay, big question here. How do I solve? How do I get x out of the exponent? Alex, we don't even need it, I promise. Let's take the natural log. Now I'm going to do it to both sides. ln, and what happens with the natural log of e to the x? It undoes, and we get just an x. And we just found x is equal to the natural log of 5/2. Okay, for this, we now have our critical number, right? This is the only one. Critical, and I'm just going to put crit. As long as I can identify it, I'm cool. That's the only critical number that we found. If I now need to know where the extrema, there's only 3 places it can happen. It can happen there at that singular critical number, or where else? It could happen at the endpoints. So there are 3 values that we need to check. So we'll say on this, and I'm trying to think of how I set it up last time. I'm just going to keep rolling here. We have extrema. If they exist, it's either going to be at f of, give me one of the values. -1 is a good choice. It might happen at f of, what's another value that we just found? The natural log of 5/2. Or it's going to happen at f of 2. Now, for your calculator here, Fern, depending, like this could be a calculator problem. It could be a no calculator problem. Your assignment tonight is without a calculator. Let's pretend it was a no calculator problem. Evaluate these and see if you can pick out the mins and maxes. That's your only job. Evaluate these 3 things. And I'm going to remind you real quick, this, at least you can start packing up, but I'm going to keep talking. If I have e to the ln of y, it's just y. These undo each other here as well, just like these undid each other. This is your way to solve this equation by hand. Do it without a calculator first, and then we'll see if we can make sense of which number is the biggest. If we can't, then we'll have to do something else. But I'll see you guys tomorrow.